Hello, I'm Professor Ruiz. I teach at UNC Asheville in the Department of Physics, and I would like to share with you our inquiry arc framework, which we are implementing in a series of pilot courses this fall 2012. Our goal is to enhance critical thinking by drawing attention to the stages that one goes through when one wrestles with a problem, whether it be in physics, history, or the arts. So we have here 4 steps: the inquire phase, the apply phase, reflect, and communicate. I want to illustrate this for you with a very, very simple problem, one that we're all familiar with, and that's driving from one city to another. So my daughter Frances leaves Asheville at 12 noon, and she travels to Greensboro to see her brother, and she drives at 50 miles an hour on the average, which includes a stop or two and not exceeding the speed limit. When she gets to Hickory, her odometer reads 75 miles. When she gets to Statesville, it reads a little more than 100 miles. When she gets to Winston-Salem, it reads 150 miles. And when she arrives at her brother's home in Greensboro, it reads 180 miles. The question is, leaving at 12 noon, traveling at 50 miles per hour, when does she reach Winston-Salem 150 miles away? Well, at the dinner table, we could work this out and say, hey, we're going 50 miles an hour. I guess, let's see, 50 miles in 1 hour. That's 100 miles for the 2 hours. And if we go 3 hours, it's 150 miles. That's Winston-Salem. That's it. 3 hours. We'll get there at 3 p.m. Well, let's analyze this in terms of the inquiry arc model. And to do that, we will list the information much like first reading a word problem, say in math or science. And here we have Frances leaves Asheville in her Camry at noon. Hickory is about 75 miles from Asheville. Statesville is about 100 miles from Asheville. Winston-Salem is about 150 miles from Asheville. And she drives on to see her brother in Greensboro, about 180 miles from Asheville. She averages 50 miles per hour. What time did she get to Winston-Salem? Now, the first point in the inquiry arc is that there is a question that's asked first. That's inquire. You may ask the question yourself. Your boss may ask the question for you on a job. A friend may ask you the question. So a question is asked. And I'm going to break this down into 3 parts where first I want to make sure I understand the question. I think we all have the experience of taking an exam and misreading a question and then answering the wrong question. So make sure the question is clear. Second, what is given? I put given here in capital letters because a lot of this stuff here I don't really need. Even though it's given, I don't really care that she drove in a Camry. That's not relevant. What's relevant here is Winston-Salem's distance from Asheville to 150. This is relevant. Leaving at noon and 50 miles per hour. And third, what principles do I need to solve the problem? What model will I use? Now, in this particular case, the equation or the principle is clear-cut, but in some disciplines, it may not be. There will be uncertainties and, that you need to deal with. So here, we summarize this result for the inquire stage. The question is, when does she reach Winston-Salem? And the given here, the relevant given, is the start time at 12 p.m., the distance of travel, 150 miles, and the velocity, 50 miles per hour. The principle is the formula distance is the velocity times the time, but that formula is implied in this single rate up here. When you say 50 miles per hour, you actually mean this equation. Think about that. If you go at 50 miles per hour for 1 hour, you have 1 hour t times 50 is 50 miles. If you go 2 hours at that rate, it's going to be double this. See, you multiply 2 times 50. See, there's the 2 times 50 to get the 100. And if you go 3 hours at 50 miles per hour for 3 hours, you then triple this. So this formula is a formal way of writing what's implied in that rate. So we go to the next step, the apply stage, where we work out the answer. We do the calculation. Here I'm going to use the formula, distance is velocity times time, and just plug in the numbers, 150 for the D, 50 for the V, and what number times 50 gives me 150? Well, that's 3. You can see that formally by dividing the 50 into the 150 and get the 3. Think of this equation here as being balanced, and if I divide both sides by 50, the 50 cancels over here, freeing up the t, and 50 into the 150 gives me the 3 hours. I add the 3 hours to the 12 p.m., and the answer is 3 p.m. Now, you might think we're finished, but we're not. A scientist is not finished when we get an answer. We need to reflect on the answer. It's a very, very important stage. Is the answer reasonable? Now, you can catch a lot of mistakes this way, because often we can make a mistake by flipping things, getting confused, dividing the wrong way. And if you do that, let's say you interchange the 150 and 50, which can be done in an application. We use an equation. You get 50 over 150, you get the 1/3 instead of the 3. You flipped it. So you get the 1/3. And then 1/3 of an hour is 20 minutes. When you add the 20 minutes to 12, you get 12:20. But see, if you ask the question of the reflection, you reflect on your answer. You're asking here, is the answer reasonable? By reflecting on that answer, you immediately see that your answer is wrong. There's no way you're driving from Asheville to Winston-Salem in 20 minutes. Then you can go back and fix things. Now, that reflect stage is very, very subtle, and it's not clear-cut. There's no clear-cut way to check your answer. That takes a lot of practice and experience. I look at the reflection stage as a certification stage. I want to certify that my answer is correct before I turn in my exam or answer a question on homework. In areas of physics where we do labs and make measurements, another part of reflection is how accurate is your answer. For example, you say 3 hours, but what do you mean? 3 hours plus or minus a few minutes? See, we could be off. It could be 3 hour, 3:03, or 3 minutes before 3 o'clock. So that's another important part of reflection. What's the uncertainty? We don't mean 3 o'clock exactly on the dot. Where she's there, and then Winston-Salem is not a point, for example. You mean the center of Winston-Salem? See, so these things would be taken up during reflection, the reflect stage. And also, reflect can be very philosophical. What's the meaning of the equation? Or how does physics relate to the real world? How does physics relate to music or psychology and perception and other areas that we'll study in our class? So reflection can be very, very broad. Finally, we communicate our answer. We don't keep it to ourselves. We tell someone in class, or we give it in a homework problem or a exam, for example. Now, in our class, we won't do formal presentations, but in other classes, you might have a PowerPoint presentation and communicate, that way. In an art class, discussion of a painting, say, or an art project, or a piece of music, a performance, or a dance. The communicate can take many, many forms. I'm going to give you some questions in homework where I'm going to challenge you to communicate some of the ideas we discussed in our class. How would you communicate them, say, to your grandmother, assuming she's not a rocket scientist, and give you some choices and see if you can pick out the best way to communicate the physics to someone that's not in the course, for example. So I hope you enjoyed this analysis to sharpen our attention here to what critical thinking is that's going on, the reflection stage. Is my answer reasonable? It's this critical thinking. So we have inquire, apply, reflect, and communicate, the inquiry arc framework. I hope you found it interesting and find it useful.